All right, so here we are looking at the energy levels in different atoms. And we start off with the mercury atom. If an electron is in the H energy level, what is the lowest photon it could possibly, lots of spelling errors in this one, emit as it travels back down to the ground state? So this one here, the lowest energy level the energy transition you're going to see is go G to F. Remember that if you're starting at H as an excited electron, you have different options. You could go all the way back down from H to A, or you could take some steps. And then here, the smallest one we're going to see is from G to F. And that is a difference of 0.2 electron volts. That's the energy of this photon. And we're asked to find, oh, there you go, the energy of the photon, 0.2 eVs. Calculate the wavelength of this emitted photon. Great. Well, E equals hc over lambda, or lambda equals hc over E. If I want to calculate that, on your formula sheets, there's actually a handy-dandy h times c number, or you could just do it individually. 4.14 times 10 to the negative 15th eV seconds times 3 times 10 to the 8th meters per second all over 0.2 EVs. And the wavelength then is 6.21 times 10 to the negative 6th meters. Or, or 6,201 nanometers. Both work. And that makes sense. It's such a high wavelength because it's a very low energy photon. How much is its frequency? Well, let's do C equals F lambda, or F equals C over lambda. Remember, this is inside the atom, so we were talking about a vacuum, and then we can use C for the speed of light. 3 times 10 to the 8th, all over the wavelength, 6.21 times 10 to the negative 6th meters. You could also use E equals HF here and figure out your F. And I got 4.83 times 10 to the 13th hertz. When the atom is in the ground state, determine the wavelength of a photon that would ionize this mercury atom. So now we've got an electron right here in the ground state, and we want to send this out. So it needs to go to ionization. And that means we need to take in 10.38 electron volts. Has to be the photon that's going to do that. Anything else would also work. So really, I should say the minimum energy, or the first largest wave, what would that be? Yeah, largest wavelength photon that would work. So then I just set 10.38 EV, E equals hc over lambda. Lambda equals E over hc divided by 3 times 10 to the 8th meters per second times 4.14 times 10 to the 15th equals what's that? Scientific notation. 1, 2, 3, 4, 5, 6. 8.36 times 10 to the 6th. Oh, negative 15th. That doesn't make any sense. Thank you for watching. It's always good to question your and see that, wait, I need something in the nanometer range. So if you made a mistake, always good to check that out. Lambda equals E. Let me look at what that is. Oh, lambda equals hc over E. You probably caught that before I did, but I'm going to keep that in. Because if you're going too fast, then you're always going to have a problem. So let me try that again. 3 times 10 to the 8th times 4.14 e negative 15th divided by 10.38. There we go. Lambda equals 1.20 times 10 to the negative 7th meters, or 120 nanometers. A very small wavelength, which makes sense. This is a high energy photon that's going to cause us to jump such a big energy level from the ground state all the way out of this mercury atom. But a photon like that, which is in the ultraviolet range, could do that. So that's the first page of this. Try the second page on your own, talking about hydrogen, and check back tomorrow as we go over this.